Hello friends, welcome to the online lecture series of Basics of Computer Network. We are studying unit number 1, that is data communication and network models. Let's have a quick revision. In last lecture, we have studied about multiplexing. That what is multiplexing? What are the types of multiplexing? As like your frequency division multiplexing, wavelength division multiplexing. These two multiplexing, it comes under a category of analog multiplexing. And third type we studied, that is your time division multiplexing, which comes under a category of what? Digital multiplexing. After that, guys, we have studied the analog transmission of signals. That is analog to analog conversion and digital to analog conversion. In analog to analog conversion, guys, we have studied about amplitude modulation, frequency modulation, and phase modulation. After that, in digital to analog modulation, we have studied ASK, which is analogous to what? Amplitude modulation. When you have a digital data, then you have to convert it into what? Analog form. So for that, you have to use a modulation ASK, FSK, that is your frequency shift keying, in which frequency it is going to change. And last is your PSK, that is your phase shift keying. In that phase of the carrier wave, it is going to change. Today's topic is your digital transmission of signals. It means we are going to study digital to digital conversion and analog to digital conversion. Now guys, for a computer, we have a digital data or binary data in this form of what? 1 and 0. So we have to encode this signal, digital data, into a digital signal, or binary data into a digital signal. So for that purpose, guys, there are three types of techniques are there: line coding techniques, block coding, and scrambling. So basically for you guys, we are going to study line coding. That is process of converting your binary data or digital data into digital signals. Now, what are the design considerations for this line coding scheme, guys? Now, baseline wondering. If you have a long strings of zeros and ones, then there may be a drift in your baseline. Also, for continuous value of your zeros or 1, it is going to introduce a DC component, that is a direct current. So, a low frequency which could not be passed through a transformer or a telephone line. Self-synchronization. Guys, it may happen that sender and receiver, they have the clock circuitry which are not synchronized. So it may happen the clock rate of sender or transmitter, it is much faster as compared to your receiver. So if this mismatch, it is, or vice versa, if this mismatch it is going to occur, then whatever the data it is being transmitted at the transmitter, maybe the receiver it is not going to recognize that data, whether it is a 1 or 0. So self-synchronization it is must. And there should be a built-in error detection, whether the data it has been detected, it has error or not. Due to this line coding, guys, what happened? There is an immunity to this noise and interference when we are going to convert digital data into your digital signals. So you can see from this figure that see the lack of synchronization. So if data 1 it has been transmitted, see, it is going to be transmitted, but it is for what? 1 bit, whereas the receiver it is going to take it as for the 2 bits, and see in the mid of the bit, second bit, it is going to make a transition, this clock circuitry. So it may happen that 0 it is being transmitted for this clock pulse. So it get confused whether it is a 1 or whether it is a 0, right? So this kind of problem, which leads to what? Lack of synchronization, so that the receiver can't understood that if 1 it is being transmitted, then the receiver should take it as a 1 or 0. So this is the problem. So that is overcome in your line coding. Now, what are the line coding schemes? There are basically 5 types of line coding schemes are there. First is unipolar, that is non-return to 0. Polar, in which it comes NRZ, non-return to 0, RZ, biphase, that is a Manchester and differential Manchester. Then it is your bipolar AMI, alternate mark inversion and pseudo-ternary. Then multi-level, multi-transition. So guys, basically we are going to see the 3 just basic types of it. We are not going into go into the details of it. Now, first is your unipolar scheme. Unipolar in the sense what? One polarity, as its name suggests. So you can see that it is non-return to 0, NR unipolar NRZ. Non-return to 0 in the sense, guys, what? If a logic 1 it is there, then it is going to be represented by high voltage. So during this bit interval, single bit interval, it is not going to make any transition. It is not coming to 0. So that's why it is called non-return to 0. Whereas for 0, we are going to represent it by 0 voltage. Similarly, next bit it is 1. So it is going to be represented by plus V voltage. Since again logic 1 it is there, we are going to take represented by plus V voltage. So it is a unipolar, because polarity it is either positive or it is what? 0. So if consistent or continuous values of zeros and ones are there, then what is going to be happen, guys? It is going to show you the continuous 0 voltage. And if it is 1 it is there, it is going to show you the continuous 1. So due to which what is going to be happen? The DC component it is going to be introduced, which is not can't be passed through a microwave or transformer. And remember, consecutive zeros and ones, they are hard to be synchronized. So we required a separate line for a clock pulse for transmitter and receiver purpose. Now next it is your polar scheme. So polar scheme basically in the sense 2 polarity, 2 voltage levels are there. So the problem of the DC component that we are talking, it is alleviated or it is eliminated. So we can see that for the polar, there are 3 categories: non-return to 0, return to 0 and biphase. Non-return to 0, again it is classified as NRZL, that is level, and NRZI, that is invert. And biphase, it has 2 types, that is a Manchester and differential Manchester. So we would have a quick idea about all these schemes. Now, polar NRZ. Polar NRZ, it is of 2 types, that is NRZL, that is a non-return to 0 level, and NRZI, that is non-return to 0 invert. So for NRZL, the level of the voltage, it is going to determine the value of the bit. So it may happen that 0 bit it is represented by the positive voltage, and logic 1 it is represented by what? Negative voltage. So it is same for all bits. Next bit it is 0. It means it is represented by what? Plus V voltage. Next bit is again it is 0. So represented by plus V voltage. But for logic 1 it is represented by negative voltage, that is minus V volt. Same for this. And at last there is a transition, because last bit is your 0. And 0 it is represented by what? Plus V voltage. Now NRZI. So basically inversion or the lack of inversion, it is going to determine the value of the bit. So if you want to see it over here, that first bit it is your bit 0. So if it is 0, see it is represented by what? Plus V voltage. And if next bit it is a 1, then it is going to make a transition. So earlier it was what? Plus V voltage. So it is going to make a transition for what? Negative voltage. But if next bit is 0, there is a no inversion. Remember, Again for next bit it is 0, there is a no inversion. But when the next bit it is a 1, then there is a transition. Right? So transition, earlier it was negative voltage, now it is represented by what? Positive voltage. So always remember guys, for this non-return to 0 invert, for bit 0 there is no inversion, but for when the next bit it is 1, there is an inversion, there is a transition. So now next bit it is a 1. So earlier it was what? Plus voltage. So now it is going to make a transition for the negative voltage. Again next bit it is 1. 1 in the sense what? Inversion. So earlier it was what? Negative voltage. Now it would invert and it would be positive voltage. But for 0 bit, no inversion it is there. So hope so you understood your polar NRZ. Now in polar NRZ, the baseline wandering problem, almost it is there both in NRZL but NRZI. But in NRZL, it is much more severe. Similarly, synchronization problem it is there, which is more serious case in your NRZL. So both have a DC component problem. So RZ, in order to overcome those disadvantage, we are studying RZ, that is a return to 0. Now return to 0, it is going to provide you the synchronization for consecutive zeros and 1. A return to 0 in the sense what it means guys, the signal it is going during the half bit interval, it is going to make a transition. It returns to 0. For earlier case, what we have seen, for each bit duration, the level it is not going to change. That because it was NRZ, non-return through 0. But since it is returned to 0, for each bit it is going to make a transition at the mid of this duration of this single bit. So signal changes during each bit. And 3 values we can use it for, that is a plus, minus and zeros. So bit 1, there is a transition positive to 0. See the transition positive to 0, positive to 0. And for bit 0, it is negative to 0 transition. You can see it over here. Earlier, initially it is a negative, then it comes to 0. Similarly, it was negative, comes to 0. Again, 0 it is represented by transition, negative to 0. Whereas logic 1 is represented by a transition positive to 0. So the problem of synchronization, it is being solved, and the problem of this DC component, it has been solved in your return to 0. Now biphase, combination of RZ and NRZ, it is combined together, that is L, and the signal transition at the middle of the bit is used for synchronization. So it is of 2 types guys. Manchester, that is used for Ethernet LAN. So in Manchester coding, bit 1 it is represented by negative to positive transition, and bit 0 it is represented by positive to negative transition. So remember this thing. And second one, it is called your differential Manchester, and its application it is for token ring LAN connection. So in differential Manchester, bit 1 it is going to represent no transition at the beginning of a bit, and bit 0 in the sense transition at the beginning of a bit. So now you can you will get the idea from this waveform now. Manchester, see that 0 it is represented by a transition from positive to negative guys, since it is a polar, right? And logic 1 it is represented by negative transition to positive. Next bit is 0, so it is going to make a transition from positive to negative. Again bit is 0, so as we told that 0 it is represented by a transition from positive to negative, but 1 is represented by transition from negative to positive, so it is negative to positive. Similarly, it is bit 1 negative to positive. So hope so you understood this Manchester coding. Now moving towards the differential Manchester. Now as we told that there is a no inversion if next bit is 1, and if next bit is 0 then there is an inversion. So since we are assuming that initial the bit it or voltage it was positive, and when the next bit it comes a 0, it had made a transition that is from negative to positive. And since over here next bit it is 1, so there is no transition at the beginning, remember. So that's why no transition at the beginning, and then at the mid of this bit it makes a transition. Since next bit is 0, so it is going to make a transition at the beginning itself. Earlier it was what? Negative. Since next bit it is a 0, then it is going to make a transition that is from positive to negative. Similarly, next bit is 0. Again it is going to make an inversion that is positive to negative, because earlier it was negative. So it is going to now make a positive to negative. But next bit over here it is a 1. So as we know, no inversion. So that's why at the initial no inversion it is there. So this negative voltage it is taken as for the half of the bit duration, would remain negative. But at this mid it would go to positive. Since next bit is 1, again at the initial stage, at the beginning no transition, the positive it is going to taken along for the half bit duration. And after this half bit duration, it makes a transition from positive to negative, which is called as what? Differential Manchester. Understood, guys? Now, the next it is called a bipolar scheme. In bipolar scheme, guys, there are 3 levels of voltage: positive, negative, and 0. So in this one, basically it is of 2 types, that is AMI, that is alternate mark inversion, and pseudo ternary. So in alternate mark inversion, what is going to be happen? Bit 0 it is represented by what? 0 voltage. Whereas bit 1 it is represented by alternating positive and negative voltage, that is plus minus 1. So if next bit is logic 1, it is going to be represented by what? Plus 1. But since next bit is 0, it is represented by 0 voltage. Next bit is 0, represented by 0 voltage. But now next bit is 1. So it is alternate mark inversion. So earlier for logic 1 it was positive. Now for the next logic 1 it would be represented by negative voltage. So it is called alternate mark inversion. And this is your pseudo ternary. Pseudo ternary in this what? Logic 1 is represented by 0 voltage, whereas bit 0 it is represented by alternate positive and negative voltage. It is just opposite to AMI. See over here. 0 first it is represented by positive voltage. Logic 1 is represented by 0 voltage. So next bit is 0. So earlier it was initial, it was represented by positive. Now it is represented as a negative. Since it is a negative, so next bit is 0. So it makes a alternate, it is going to make a transition. Because it is what? Pseudo ternary, opposite to AMI. So now earlier it was represented by negative voltage. Now it is represented by what? Positive voltage. And logic 1 is 0. Since earlier it was a positive, now for the next bit, that is for logic 0, it is represented by negative voltage. So hope so you understood your bipolar scheme. Now, analog to digital conversion. Your digital to digital conversion, it is over. Now if you have an analog data, you want to have to convert into digital conversion for this digital transmission. For this, you require definitely guys analog to digital converter. This is your analog signal. And by means of analog to digital conversion, it is converted into your discrete signal, that is digital signal in terms of 1 and 0. And analog information guys, it could be a voice, video, text, graph, etc. Now PCM guys, pulse code modulation. Basically we use for converting this analog to digital conversion. So over here the analog signal is sampled, then that sampled signal is quantized. So output of sampler, it is a PAM, that is a pulse amplitude modulation wave. So which is quantized into some discrete level. And then that quantized values are encoded as a stream of bits. So now we are going to see in brief now. See the output of this sampling, it is your pulse amplitude modulation. According to the Nyquist theorem guys, the sampling rate must be at least 2 times the highest frequency contained in the signal. Suppose that analog signal, continuous time signal, it has a maximum frequency. Highest frequency, it is your 4000 hertz. Then what should be the sampling rate? Sampling rate, it should be, according to Nyquist theorem, it should be at least twice of highest frequency contained in the signal. It means 2 into 400, that is a 8000 samples per second. So it is a minimum criteria guys. Basically, ideally it should be greater than 8000 samples per second. Then and only then you could be able, or you could reconstruct the sampled waveform, from you could reconstruct the analog waveform from its sampled signal. So what are the components of your PCM encoder? So you can see it is an analog signal. This is your PCM encoder. Basically it consists of sampling, quantizing and encoding. 3 blocks are very, very important. So now if you have analog signal, which is given to what? Sampling. So sampling, it is going to make a sample at a discrete instant. So at particular instant, it is going to take a sample of this analog signal. So the output of sampler, it is your PAM, that is a pulse amplitude modulated signal. So which is given to a quantizer. Quantizer, what is it going to do it? It is going to make a, it is going to assign the values to a particular window in which it is going to come. We would see this quantization. Basically this quantization, it is your, 2 types, that is a uniform quantization and non-uniform quantization. Uniform quantization in the sense the step size are constant, and non-uniform quantization in the sense what the step size are variable. So which is not in your syllabus actually guys. So we would just have a brief, introduction of this one. And after this one, what we are going to do it, we have to convert into a bits. So that by using encoding, we are going to assign some coding to these particular samples as like 110, 1110, depending on the number of quantization levels. Now, what are the different sampling methods for PCM guys? So there are 3 techniques: ideal sampling, natural sampling and flat top sampling. So in ideal sampling, what is going to be happen if you see this one? Ideal sampling, see, we have taken this dotted line, it is going to indicates the analog signal, which is represented by this dotted line. And at a particular instant, we are going to take a sample of these signals. Since the width of this pulses are tends to 0 guys, tends to 0. So that's why it is called a ideal sampling or impulse sampling. Since the width of this pulse tends to 0, the power content, the energy content of this, it is very zero, very low. So we could not use this ideal sampling for transmission, and practically it does not exist. And the rate at which we are going to make a sampling, it is denoted by the sampling period, that is Ts. So this is the disadvantage of your ideal sampling, that we could not use it because it doesn't have power to be transmitted. So we have a natural sampling. Natural sampling in the sense, guys, what? See, the top of these samples, which is shown in this pink color, the top of these samples, it is going to retain the shape of this dotted analog signal. So that's why it is called a natural sampling. But what is the problem with this natural sampling? It is that noise, it can easily be added at the top of these pulses. And when the noise it has been added, it is very difficult to remove the noise from the top of these samples, because noise it can easily add to this top of these samples. So in order to overcome, and see the width, it has a specific width, but in order to overcome the disadvantage of natural sampling, we are going for flat top sampling. Flat top means the top of these samples are flat, so that the noise it could not be easily added to this signal, this pulses. So practically we are going to use this natural and flat top sampling, and most of the time this flat top sampling, which is whose output it is taken by means of what? Sample and hold circuit. As I told, the Nyquist sampling rate, it should be the twice of the maximum frequency, highest frequency content of your analog signal. So it is always equal to twice of F max, whether it is a low pass signal or for band pass signal. This is the example that how, if the different samplings are there, then how the sampled output it would look like. So if Nyquist rate is equal to Fs is equal to 2f, see how the samples it has been taken, how the samples it look like. That is called Nyquist rate. Oversampling in the sense what? Fs it is greater than twice of ff, so we have taken 4f. So see, the number of samples it has been increased, So if the number of samples it is going to be increased, it would be very easy to reconstruct it from its sampled version. And see, it is a undersampling, means Fs less than twice of f. So we have considered Fs equal to f. So see that how it is going to look like. Minimum sample we have taken, and it is, guys, very difficult when we are going to pass this sample through this any low pass filter. It would be very difficult to reconstruct your original signal because we have less number of samples. And what I was telling about the quantization, see, it as a brief, very quick, we could understand this one. Now see, guys, this is your input signal, right? So you can see that this is your analog input signal, what I am drawing it over here. So what we are going to do it, this is your continuous analog signal, say x of t. We are going to take the samples at a particular instant, at this instant, at this instant, then at this instant, like this one. So you can see the quantization level, it has 8 levels, that is 0 to 7. So since this level, this sample value, the circled one, it has a value which is equal to minus 1.22, right? Now, the normalized quantized level, quantized level, since it is nearer to 1.5, it is nearer to 1.5, then what we are going to do it, we are normalizing this value 1.2 to this 1.50. So what is the difference? What is the error? Minus 0.38, it is the error. So what is the quantization code? Quantization code, it is nearer to this 2. See, this is the quantization code. And this is 0, minus 1, minus 2, minus 3, minus 4. This is 1, 2, 3, 4. So since it has a value that is minus 1.22, which is nearer to this minus 1.5, so we have assigned this value to minus 1.5. But this minus 1.5, it comes under the near the window of what? Quantization code, that is 2. So we have assigned a code 2. And what is the binary equivalent of 2? It is 0, 1, 0. Understood? Similarly, you can take this sample. So which is what? Which is 1.5. It is coming to plus 1.5, right? So since it is a plus 1.5, so normalization quantized value, it is 1.5 remain. So what is the difference? It is a 0. And since this value, it comes to the level, comes to the window, that is a 5. So what is the binary equivalent of 5? It is 1, 0, 1. So that is your coding. Similarly, next sample you can observe it, that is your 3.24. It is a 3 and 4. It comes near to 3.4. But since it is nearer to 3.5, so we have assigned this 3.24. The normalized value we have assigned is 3.5. So what is the difference? 3.5 minus 3.24. It is a 0.26 error. It is there. And since it is nearer to this window, that is a 7, we have assigned a quantization code, that is 7. And what is a binary equivalent of 7? It is what? 111. And hence, guys, it is for all the sampled signals. You can take this sample. See, it is nearer to minus 2.6. This is minus 2. And it is minus 2.6. And minus 2.6, it is nearer to this minus 2.5. So we have assigned this code minus 2.5. What is the difference? It is a minus 2.4. And since this value, it is going to nearer to this code 1. So we have assigned this minus 2.6 to the code 1. And what is the binary equivalent of 1? It is 001. So understood, guys, quantization. And remember, it is a uniform quantization, because the spacing between these levels are same. That is 1, 2, 3, 4. The step size is constant. So hope so you understood one. And last, it is your classification of transmission media. So basically it is not in your syllabus, but still transmission media, it means what? The way by which we are going to send the data. So it is of two types: guided, that is called a wireless, and unguided, it is means your wireless, that is your free space. And what does the guided? Guided, it means it has two types, three types: twisted pair cable, coaxial cable, and fiber optic cable. So as you know, the fiber optic cable, basically it is used for these light signals. It has a speed of 3 to 10 raised to 8 meter per second, very fast. And nowadays the network, the internet network, it is going to be led out by this fiber optic cable. Coaxial cable, it has a much more speed as compared to your twisted pair cable. And the noise immunity of this coaxial cable, it is very, very good as compared to twisted pair cable. And the bandwidth of coaxial cable, it is much more greater than that of your twisted pair cable. But fiber optic, it is the best. Although it has a more cost of its implementation, but the noise immunity, it is very, very high. Noise distortion is almost zero. So guys, today we have studied the digital transmission, analog to digital conversion and digital to digital conversion. In digital to digital conversion, we have seen the line codes. That what are the types of line codes? Unipolar, polar, bipolar, biphase. And in analog to digital conversion, we have seen these things. That how the sampling, quantization and encoding, it is going to help us to convert your analog to digital conversion. So this is the assignment number 4. Please note down this assignment. Next module in which we are going to discuss about it, noise types, then Shannon-Hartley theorem and channel capacity, and what is Nyquist rate. This is my email address. Please note it down. And it's all about our today's lecture. Thank you very much, guys. Have a great day.